In this video, we'll be discussing chemical reactions. Chemical reactions occur all around us and are responsible for many processes we see every day. This is mainly because of the fact that all materials are made of chemicals, and chemical reactions happen when two or more chemicals, known as reactants, interact and bonds are broken and repaired, which makes new compounds or elements called products. These new products are observed and often used in the world. An example of this would be observing a burning flame and applying this to a barbecue grill, in which propane and oxygen interact in the presence of heat to produce water and carbon dioxide. We will further explain similar examples and go into depth about the types of chemical reactions. In chemistry, there are 5 general types of chemical reactions. These include single replacement, double replacement, combination, decomposition, and combustion. First, we start with a single replacement reaction. I'll demonstrate how a single replacement reaction works with the letters A, B, and C. First, we have reactant A plus reactant BC. And this must yield all of the reactants, just they're in a different form. So there would be A, B, and C would all be appearing, just not necessarily in this order. So in a single replacement reaction, a single element is being swapped with another single element. So A would be replaced with B and B would be replaced with A. So here we have A, B, and C. So this and this would flip positions like this. So this would be rewritten as B, A, and C, in which A and C would become the same and B would be alone. So the products would be B plus AC. An example of a single replacement reaction would be the rusting of galvanized steel, which is written in the equation Fe2 plus 2H2O yields FeOH2 and 2H2. Now this is iron, water, iron hydroxide, and hydrogen. Now many might not see how this can be an example of a single replacement, but if we break down the reactants into simpler things, we can see that iron 2 stays the same, but water can be broken into HOH, which you can notice this is hydroxide and this is hydroxide. And if you single replace this, you could split the hydroxide into one thing and the hydrogen into one thing. So the iron and the hydroxide flip places to form iron hydroxide, which is here, and the product hydrogen, because if you leave hydrogen by itself, hydrogen. Next, we have a double replacement reaction. This will be demonstrated by the letters A, B, C, and D. In this, a double replacement reaction, 2 elements are being switched. So in this, AC will be switched like this. So the A will take C's position and C will take A's position. And this changes 2 different things. Changes what the B and the D are with. Therefore, it is a double replacement reaction. And this yields the products AD plus CB. As you can see, the order to start goes blue, green, and to end it goes blue, green, which means it is a successful double replacement reaction. An example of a double replacement reaction would be antacid tablets neutralizing stomach acid. This is the antacid tablet, which is calcium hydroxide, and this is stomach acid, which is hydrochloric acid. In a double replacement reaction, 2 things are being swapped. So, from the previous example with A, B, C, and D, we know that the blue would be the first, and the green would be the second of each reactant. And we know that the 2 blues replace each other. So, calcium would go next to chlorine, making CaCl2, and this hydrogen would go next to the OH, making HOH, which before we found out commonly is water. So, with this, we have CaCl2 plus H2O, already provided in its balanced form. Next, we have a decomposition reaction in which the reactants are broken into smaller items. To explain this, we'll start with the letters AB. This is very simple because AB would yield A plus B, because AB as a single unit would break down into its parts AB, making A plus B into two separate things. An example of this would be the decomposition of hydrogen peroxide, which is H2O2. And from what we know about decomposition reactions, we determined that H2O2 would be broken down into simpler products. So from this we can see H2 and O2, we could see H2O, and we could figure out that it could probably be broken down into one of those. So in this reaction, when it decomposes, O2 is being released from the H2O2, hydrogen peroxide. So we are left with the products H2O and O2. A combination reaction is almost like a decomposition reaction, but backwards. So instead of something becoming into two simpler products would become into one greater product. So again, using the letters A and B, we can conclude that A and B combine to make AB. An example of this would be the formation of water. So H2 plus O2 would make H2O. As you can see, two simple products combine to make one new product, which is larger, a compound. The last of the 5 types of chemical reactions is combustion. And combustion is special because it happens with carbon, hydrogen, and oxygen producing or using heat in the process. And this can't be described with the letters A, B, and C because it's so unique, because it's only carbon, hydrogen, and oxygen. So you have the CH and O's, and this always produces CO2 and H2O. This is a complete combustion reaction, not necessarily just CHO with no subscripts, but this is just an example of the carbon, hydrogen, and oxygen all reacting to make CO2 and H2O. In a combustion reaction, there can be an incomplete combustion reaction in which there's a weak presence of oxygen, which yields H2O as normal, but instead of CO2, it yields carbon monoxide and carbon. And this is bad because carbon monoxide is a very poisonous gas. An example of combustion would be the combustion of gasoline in a car, in which we could see the carbon, the hydrogen, and the oxygen all producing carbon dioxide and H2O, which is a complete combustion reaction. Throughout the video, you may have noticed some numbers in front of reactants and products. And what this is this indicates how much of each reactant or product you need to obey the law of conservation. And the law of conservation is the fact that all matter cannot be created or destroyed. So if you start with a certain amount, you must end up with that certain amount also. You can't just create or destroy matter at any point in time. Here we have an example of an imbalanced equation in which coefficients must be added on the outside, which were numbers on the outside positions, in order to make the law of conservation of mass exist in the equation. So we know that this is a combination reaction in which hydrogen gas and oxygen gas produce water. But from this, we see that there is, on the left side, we have hydrogen, which has 2, and oxygen, which has 2. But on the other side, hydrogen has 2, and oxygen has 1. This is a problem because we started with 2 oxygen, so we need to end up with 2 oxygen on the other side. In order to do this, we can add coefficients somewhere. And where we can add coefficients is easy to determine. Since there's 4 here and 3 here, we need to add a number. We could add a 2 here, and this makes 4 hydrogen on this side and 2 oxygen on this side. But then this side is unbalanced, and hydrogen has 2 and oxygen has 2. So we can add a 2 here. So now we have 4 hydrogen on this side and 2 oxygen on this side. And look, on this side we have 4 hydrogen and 2 oxygen. Therefore, the equation is balanced and the law of conservation of mass is followed. As you can see, chemical reactions occur all around us and are responsible for many processes we see every day. The single replacement, double replacement, decomposition, combustion, and combustion reactions are all relevant to everyday life. The single replacement, which has one element being replaced. Double replacement, which has 2 elements being replaced. Decomposition, in which one thing is broken down into 2 simpler things. The combination, which is a combination of 2 simpler things into one bigger thing. And the combustion, which is the carbons, hydrogen, and oxygen being burned in a process in which makes carbon dioxide and water. Thanks for watching.